Okay, good morning, gang. Welcome back to Honors Calc 1. Today we're going to do a few things. So Thomas is going to walk us through the product and quotient rules. Before we do that, I want to address one thing from the textbook that I feel really isn't handled well. And that's how we define the number e. So before I hand the reins over to Thomas, we're going to do a little bit of a short lecture here on the number e as it's defined in our book. This is MAC2311, section OH1. And today is the 27th, I think. So today, Thomas will teach us the product and quotient rules. First, though, the number e. Which we know is irrational. It's like 2.71828 blah, blah, blah. It's a transcendental irrational number like pi. It's a special number because it's the base of the natural exponential. Like we saw from Tahara's lecture yesterday, the derivative of e to the x is e to the x, right? And this is what makes, this is why e is special. But how do we define the number? Our book defines e as the unique number, and Tahara talked about this, the unique real number satisfying limit h to 0, e to the h minus 1 over h equals 1. That's the definition that our book uses. But most people, most books, including probably your pre-calculus and college algebra books, define e as the limit as n goes to infinity, 1 plus 1 over n to the n. All right, they say this is the definition of the number e. And that second definition is way more manageable. I'll show you here, because it comes from compound interest, right? As you send the number of compoundings to infinity in the compound interest formula, which this, looks very much like. I should use x's here so I don't confuse Desmos. This is the normal way of doing it. And if I add in here the line y equals e, you'll see as we wander further and further and further to the right, the red graph approaches that blue horizontal asymptote. So this is the normal way of defining the number e. And what I wanted to show you is that our way is really the same as the normal way. So this is the book's definition. This is the normal definition. Now I aim to show you that they're the same. To see that these are the same, substitute h for 1 over n in the first definition, in our book's definition. Observe that for h to go to 0, we need n to go to infinity. So if lim h to 0, e to the h minus 1 over h equals 1, that means the same thing as saying e to the h minus 1 over h is very close to 1 for h very close to 0, right? If h gets really, really close to 0, then this thing should get really, really close to 1. That's what it means to say the limit of this thing is 1. This is the same as saying, now I'm going to do my substitution. E to the 1 over n minus 1 divided by 1 over n should be very, very close to 1 for n very close to infinity, right? For really, really big numbers, n. Because if h is 1 over n, for h to be close to 0, n needs to be really big. Now we're just going to play with this expression using algebra. I'm going to come over here. If I multiply both sides by 1 over n, this will become e to the 1 over n minus 1 is approximately equal to 1 times 1 over n. Well, that's 1 over n, again, for large n. Now I add 1 to both sides, and I get e to the 1 over n is approximately equal to 1 plus 1 over n, again, for large n. And now I'll raise both sides to the nth power, and I get e is approximately equal to 1 plus 1 over n to the n, again, for big values of n. And this is the same thing as saying that e is equal to the limit as n goes to infinity of 1 plus 1 over n to the n. So these really are the same, right? Your textbook's definition really is the same as the old-fashioned definition. And I just wanted to verify that. The reason our textbook uses the definition it does the lim h to 0 e to the h minus 1 over h equals 1 definition is because if f of x is equal to e to the x, then f primed of x is lim h to 0 e to the x plus h minus e to the x all over h. And then I can use some algebra here to rewrite this as lim h to 0 e to the x times e to the h minus e to the x all over h. And then a little more algebra, I factor out an e to the x, and you get e to the h minus 1 over h times e to the x, like this. And then by the definition of e, this is lim h to 0 e to the h minus 1 over h times e to the x. By our definition, this is 1. So this is just 1 times e to the x, which is e to the x. So the reason our book uses this wonky definition, the purpose of that is to allow us to readily show that the derivative of e to the x is e to the x. And I just wanted to, again, verify that this definition is equivalent to this definition. They really say the same thing. So that was all I wanted to do for you guys today. The rest of the day is going to be Thomas's. He's going to show us the product and the quotient rules. Did anybody need to see any part of this again? Good. might be able to sneak in most of it here if you want a screenshot. So here's the equivalence of the two definitions. And then here is the reason we like the other definition, the definition that we're using, the kind of wonky one. We like that because it's precisely what you need to show that e to the x is its own derivative. Now, Thomas is going to be doing a live lecture today. I'm going to go ahead and make him a co-host so he can share his screen. There we go. And I'm going to hand it over to you now, Thomas. So you might want to unmute yourself before you start talking. Instead of holding the space bar, you can just unmute for the whole time. You should be able to screen share, and you are good to go now, buddy.
Okay. Why is my camera not working? That's strange.
That's all right. Take your time.
Perfect.
All
okay.
right. Here, let me turn. I bet I have to turn my share off. There we go. Now you should be able to screen share. I'm sorry. So I can see .cam. It looks good. Just go ahead and turn on the screen share, and everybody should be able to follow.
Screen share. Screen share. Is that not? Wait,
There we go. Perfect. All right. So we've got, it looks like you're going to have to change the camera. Your screen share is using the one camera. And then if we swap it, perhaps looks like.
It's because if I change my Zoom camera to my face, it'll work.
Okay. Yeah, these sort of things can be a bit of a hassle, but it looks like it's going to come out just fine.
Why is this not working? Stop screen sharing for a second and change my video camera.
Yeah, if you select
to my front camera,
change to that. Yeah.
Is that working now? Let me switch this one. Okay, is that better?
Let's see. So it looks like, right, go ahead and turn on your screen share. Let's see what we get.
Okay. Screen share, camera, share.
There we go. Beautiful. Yeah, perfect.
Okay. So I'm going to teach you about the product and quotient rules. First one I'm going to teach you about is the product rule. So for both of these, the product rule deals with multiplication. That's just a basic multiplication definition. The numbers, when you multiply two numbers, the answer is the product. So you can just put these, you can like equate these together, like product rule deals with multiplication, and the quotient is the answer when you divide two numbers. So the quotient rule is going to be division. So here is the definition of the product rule. The derivative of a product of two functions is the derivative of the first function times the second function plus the derivative of the second function times the first function. This definition is pretty long. There's an easier mnemonic that you can use to like remember this better. It's called the derivative of the first times the second plus the derivative of the second times the first. It's a lot easier, so I'll give you guys a minute to copy both of those down. This is the easier way to remember it. If you took a calculus class in high school, you probably have heard this mnemonic before. And so there are two ways that this rule can be written. There is the Leibniz notation, which can be written as such: d over dx time of f of x times g of x equals f of x g of x times g of x plus g of x d over dx times f of x. So we see here the derivative of the first, f of x, times the second, g of x, plus the derivative of the second, g of x, times the first, f of x. There's an easier notation that I prefer, which is prime notation. Prime notation has it as such: f times g prime. So it would be f prime times g plus g prime times f. So derivative of the first, f, times the second, g, plus derivative of the second, g, times first, f. Just like that. So why doesn't f of g, or f times g, equal f prime times g prime? It's because you have to treat this like a polynomial. So basically, if you just treated it like this, anytime you multiplied, say, let's say f equals 5 and g equals 3x, if you did it like this, it would be the derivative of f would always be 0, and the derivative of gx would be 3. And so every function times a constant would always be 0, because the derivative of a constant is 0. So that's why it's like that. So I have a proof for you. I have a proof for everyone for the product rule. Does anyone have any questions so far about everything that's been covered?
Looking great. Looking beautiful so far.
Okay. So I have this proof. I'm just gonna move that down. Okay. So let's say that capital F of x equals f of x times g of x. That's how product rule is for multiplication. So you're multiplying two functions. So the derivative of f prime of x would be, as the limit approaches 0, this is the definition of derivative. We know that f times f of x plus h minus f of x all over h. So when you plug those in, you'd plug it in as, so since f of x equals f of x times g of x, in this case, f of x plus h would be f of x plus h times g of x plus h minus f of x times g of x all over h. And then you can multiply these and you get these four terms on top. So the limit of, as h approaches 0, would be f of x plus h times g of x plus h plus f of x plus h times g of x minus f of x plus h times g of x minus f of x times g of x over h. And you don't want to cancel these two out. You could easily just cancel these two, but you don't want to. You'll see on the proof. You're going to group these together. So group 1 is going to go with group 3, and group 2 is going to go with group 4.
Very nice.
So group them like this as the limit h approaches 0. F of x times f of x plus h times g of x plus h minus f of x plus h times g of x. So you have your first function paired with your third function, and you have your second function with your fourth function over here, f of x plus h times g of x minus f of x times g of x over h. And then you can factor out an f of x plus h from this side. You can factor out a g of x from this side, and there's a pattern with these two. So notice how the definition of a derivative is f of x plus h minus f of x all over h. So you see that pattern here, and you see that here. So once you factor those out, you get this function. So f of x plus h is just going to be let me move this up. F of x plus h is the function times the derivative. This is the definition of a derivative as we've learned, times the derivative of g of x plus g of x times the derivative of f of x. So that is a proof of how this equation works. Does anyone have any questions about this?
Yeah, this is a very clever proof. So the sneaky trick here, in case anybody is wondering, if you look back at the item of the line there with the circles, items 1, 2, 3, and 4 in that big fraction, items 2 and 3 we added and subtracted the same quantity. So this is like the add zero trick, where we sneak some shit in by adding that thing and subtracting that thing. So it doesn't change the value of the expression. But then when we regroup the terms, we're able to get the pieces out that we want. So what Thomas has run through here is sort of the standard proof of the product rule, and it's a very nice proof. If you want to see more about this, you can go to Paul's online math notes. It's linked in the modules under differentiation rules, and he has nice, careful explanations of where all these pieces come from and where all of them go. But yeah, very nicely done, Thomas.
So now I'm going to do some examples of how to do the product rule. So the first example I want to do, so keep in mind you don't always want to use the product rule for everything. This is just a preliminary example to get you comfortable with this rule. First notation I'm going to use Leibniz's notation. I'll do examples in both Leibniz and prime notation. So Leibniz's notation, let's say f of x equals 3x squared and g of x equals x plus 5. So what is the derivative of f of x times g of x? So to set it up, x times g of x. So it's going to be derivative of the first, 3x squared times d over dx, times the second, which would be x plus 5 plus derivative of x plus 5 times 3x squared. So then we can derive the derivative of 3x squared equals 6x times x plus 5. Derivative of x is 1, derivative of 5 is 0, and times 3x squared. And then you can just multiply these. So the answer will not, the next step would be to combine these. 6x times x is 6x squared, 6x times 5 is 30x plus, so 1 times 3x squared is 3x squared, 0 times 3x squared is 0. So your answer, g over dx of x times g of x is going to be 9x squared plus 30x. But you don't have to do it this way. You could easily just combine 3x squared and x plus 5. at the beginning and do normal derivation. So 3x squared times x would be 3x to the third. 3x squared times 5 is 15x squared. If you do the derivative of 3x to the third plus 15x squared, it's going to equal, derivative of 3x to the third is 9x squared. Then derivative of 15x squared is going to be 30x, and you get the same answer.
I'd like to
So-
pause here just for a moment if we could. Your answers are correct and there's no issue with that. But if we come up to the follow your arrow back up, the first line you have after d dx of f of x times g of x, it looks like we've written 3x squared times d dx of x plus 5 plus x plus 5 times d dx of 3x squared. But then we differentiated the pieces that are to the left of the d dx rather than the pieces that are to the right of the d dx. It turns out that it really doesn't matter here. It works out fine either way because we're differentiating one and leaving the other alone. But the normal notation there would be a little bit different. So I just want to, you haven't made a mistake necessarily, but I do want to jump in here just for a second. So I'm going to steal your screen share for one moment.
Okay.
So normally we would read this as like, we want to differentiate this piece and differentiate this piece here. And I think maybe you did the other way around where you differentiated the piece that was to the left of the ddx in each of these. And the upshot is the same thing. We're going to end up with the same result because in one of these pieces, you differentiated one function, and in the other piece, you differentiated the other function. So your answer is correct. But if anybody is having a hard time following the notation, you may want to come back and move the ddx's to the other piece, or you may want to rewrite it like this. So the 3x squared in this first line would normally stay itself. And then here we would differentiate the x plus 5 to 1 plus 0. And then in the other piece, we would have the x plus 5 and then differentiate the 3x squared. And there's nothing wrong with what Thomas did, but that notation might be a little bit confusing to someone who's reading it left to right, which is the normal way. So as a general rule, ddx differentiates the thing to the right of him, and the thing to the left just continues on. But the point that Thomas is making here on this particular problem is that f times g is still a polynomial, so we don't actually need the product rule. But I did want to jump in just for a second and point out that normally we differentiate the thing to the right of the ddx rather than the thing to the left of the ddx. But as long as you're priming one of the functions and leaving the other alone, and then you swap the role in the other piece where you prime the other function and leave the first alone, you'll come out to the same thing. You'll come out just fine. So I'm sorry for the interruption there. I just wanted to jump in case there was any confusion about the notation. I'll turn off my share and hand it back over.
Yeah, so for the product rule, you can also switch this if we go back to our original. Wait, is my screen share back on?
I think you'll have to turn it back on manually. I think when I take over it,
Oh, okay.
it's off. I'm sorry.
When we go back to, it can also be seen as, it doesn't always have to be derivative of the first times the second plus the derivative of the second times the first. It can be the derivative of the second times the first plus the derivative of the first times the second.
Very good.
As long as you're deriving f of x and multiplying it by g of x, and then driving it by g of x, then multiplying it by f of x, and however way, you should get the same answer.
Yep. Yeah, that's exactly the idea. So we differentiate the functions one at a time, and we add up the different blocks with one differentiated at a time. This is beautiful. Yeah, let's go ahead and continue. This is good.
So the next one I want to show you, I'm going to do in prime notation. So, and this is an example of why we need the product rule sometimes, why you can't just combine functions and do basic derivation. So let's have, let me see, where is it? F of x equals x e to the x. So you can't just combine these because they're already combined, and the e to the x follows its own derivation rules. So f prime to the x is going to equal derivative of the first times the second plus the derivative of the second times the first. So then from there, derivative of x equals 1 times e to the x. Derivative of e to the x is e to the x and times x. So we would multiply 1 times e to the x is e to the x. Then e to the x times x is going to be x e to the x, like that. And then we can factor out e to the x. From there, we would get e to the x equals 1 plus x, like that. So here's an example of one example of how we can use the product rule. You can use the product rule is also useful for trig functions, but we aren't going to get into that because we haven't learned that yet. We're going to do a natural log function. So we haven't learned this yet, but I got approval for this problem. So let's say that I'm going to do this next one in Leibniz notation again. So f of x equals x squared and g of x equals ln x. So d over dx f of x times g of x. So the derivative of the first function, d over dx, x squared times ln of x, plus the derivative of the second function, ln of x times x squared. So the derivative of x squared is going to be 2x times ln of x. The derivative of ln x equals 1 over x. So we're going to use that in the future, but that's just what that equals. So derivative of ln x is 1 over x times x squared. 2x times ln of x is 2x ln of x, plus you get x squared over x. Can divide that, so it's x squared divided by x is x. You can factor out an x from these, so you get x times 2 ln of x plus 1.
Very nice. So yeah, the derivative of the natural log function is something we haven't learned yet, but we will learn soon. Cooking up the derivative of ln x as 1 over x requires a little bit of something called the chain rule that we'll be learning soon. But this is a nice preview. If you know, for example, for whatever reason, that the derivative of ln x is 1 over x, then we can compute derivatives of combinations of the ln function and other functions, just like Thomas has done here. It's very nice.
Okay, so are there any questions about any of these problems?
Is everybody able to see where all the pieces come from and how they're being combined? Very nice. Yeah,
Okay.
I think you're doing good.
The next rule I want to talk about is the quotient rule. So the quotient rule is again used for division. The quotient is the answer of when you divide two numbers. So the definition of the quotient rule is the derivative. Yeah, the derivative of a quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So that is very, very long. So instead, we want to use a mnemonic for that instead. So another mnemonic that if you took a calculus class in high school, you probably learned low d high minus high d low all over low squared. So there are two notations again for this. So here's the Leibniz notation. That would be d over d of x, f of x over g of x low g of x times d over d of x, f of x minus f of x times d dx of g of x all over g of x squared. So that also seems like a lot. Not my favorite notation. I prefer the prime notation. So here is the prime notation. F over g equals g times f prime minus f times g prime all over g squared.
Very good. Yeah, and that mnemonic, that's going to be your best friend. Low d high minus high d low over low or over low squared. This rule is so complicated, we try to avoid it as much as we can. But that little mnemonic that he's giving you there is the way that 99.9% of people are able to remember this correctly.
Yep, so it would be low is g of x, so low d high f of x minus high f of x d low g of x all over low squared or low as such. And so there's another proof for this one. I thought this proof was really helpful too. So we're going to prove that deriving a function divided by like f of x over g of x equals that function just shown. So we use our definition of derivative f times x plus h minus f of x over h, but then instead of plugging in that, you'd plug in f of x plus h over g of x plus h minus f of x over g of x all over h. So then to make this easier, you factor out the 1 over h, and you get this. You would get f of x plus h over g of x plus h minus f of x over g of x. And then in order to continue with this proof, you need to multiply both sides by the denominator of the other the denominator of the other. So f of x plus h over g of x plus h times g of x over g of x minus f of x over g of x times g of x plus h over g of x plus h to give them both a common denominator.
Nice.
Moving down, you get this. Now, since they have the same denominator, you can bring them together. So g of x times f of x plus h minus f of x times g of x plus h. So we're starting to see a pattern of the low function and the derived function and the high function and the derived low function. So you can bring the h back in, and this also shows something else that's very important. Since you are dividing in this function, the h of 0 shows that you cannot, when there's a 0, you can't divide by 0. So the denominator h will always have to be greater than 0 for this to work. So you get this, and then that can be factored into this. So you have low g of x derivative of high minus high f of x derivative of low all over low squared g of x times g of x plus h.
This is more or less correct. We would need to be a little bit sneakier in that second to last line. There's going to be a necessary sort of add and subtract trick like we used in the previous guy. but we can see all the parts here. So if you look in this second to last line, you've got g of x times g of x plus h. Ignore the h for now. As h goes to 0, those two pieces will both become g of x, right? Because x plus h just becomes x. So that's where the g squared is coming from. Upstairs, the g of x times f of x plus h, if we were to subtract from that g of x times f of x, then we could factor out the g of x and have f of x plus h minus f of x. Those things together with the h downstairs will become f prime. And similarly, at the other term, if we were to add f of x times g of x plus h, you could, or f of x times g of x, you could factor out the f of x and you would have g of x minus g of x plus h. And that together with the h downstairs would give you f times g prime. So this is, we need a little bit more algebra before we can justify the proof here, but it's very, very close. And the idea that as the h goes to 0, the bottom becomes g squared, and the top becomes this difference of terms involving g and the derivative of f and the derivative of g is correct.
Okay, so now we're going to do some examples for the quotient rule. So are there any questions so far about the quotient rule?
So this
Okay.
tends to be the bane of calculus students' existence. We don't like the quotient rule because it requires so much calculation, but it is something we'll have to learn and we'll have to hold on to. And that, yeah, like Ben is saying in the chat, that little mnemonic, the low d high minus high d low over low low trig, that's a really nice thing. So I would hold on to that tight and use that when you practice your derivatives. Instead of looking up the formula and writing it down, try to remember the mnemonic, write down the mnemonic and see if you can proceed from there. All right.
So our first example is going to be something simple. I'm going to do this both in Leibniz and prime notation. So I'm going to do examples in both Leibniz and prime notation. So let's say f of x equals 3x squared and g of x equals x plus 5 from our product rule problem. So we want to find the derivative of f of x over g of x. So we have to set up like this: d over dx, f of x over g of x. So first we have our low. So it's going to be low derivative of high f of x d over dx of 3x squared minus high d low all over low squared, like that. Next step, I have to derive x plus 5 times the derivative of 3x squared is 6x minus 3x times the derivative of x plus 5. X equals 1, 5 equals 0, all over x plus 5 squared. It's better to leave this term like this, squared, rather than multiplying it all out. It makes it a lot simpler. And so we can multiply from there. 6x times x equals 6x squared plus 5 times 6x equals 30x minus 3x squared times 1 equals 3x. 3x squared times 1 equals 3x squared. 3x squared times 0 is 0. Since it's being subtracted, minus 3x squared all over x plus 5 squared. Then combine 6x squared minus 30x minus 3x, that'll be 3x squared plus 30x all over x plus 5 squared. Any questions about that?
Looking very nice.
Okay, and then I'm going to do a next one in prime notation. This is going to be a non-polynomial function, so it's going to be, let's have f equal, f of x is going to equal 3x, and we're going to have g of x equal square root of x. So f over g prime equals, so we have to set it up. F over g prime equals derivative or low, which is g of x, d high, which is 3 of x, minus high, which is 3 of x, times d times d low, all over low squared. So f over g prime equals, so we have our root x times the derivative of 3x equals 3 minus 3x times, we know that the derivative of x squared is 1 over 2 root x. We can separate that out in a different one, so d over dx, for anyone who needs clarification, d over dx equals x squared. You can change x squared to x to the 1/2. The derivative of that is going to be 1/2 x to the negative 1/2. Since it's negative, you bring it down. 1 over 2x to the 1/2. It's now positive 1/2. And then that's just going to be 1 over 2 root x, like that. All over low squared. So now f g prime. So 3 times root x is 3 root x minus 3x times 1 over 2 root x. It's going to be 3x over 2 root x all over x squared. So now in this case, we can change that so that it's, so we can make root x squared into x. So it would be 3 over x minus 3x over 2 root x over x. And then you can simplify from there. You can multiply the you can either leave it like this, or you could multiply it and make it into 3 root x times 3x over 2 root x times 1x, which would become 3 root x over x minus 3x over 2x root x, which then can also simplify to, I think that's right.
Yeah, you got it. So the 3 root x over x, you could combine the root x and the x. That's 3 over the square root of x. And then in the second term, you can cancel the x's.
Mm-hmm. So that those would be canceled, and then that would cancel as, because it would go up and be, it's a negative, or if it's 1/2 minus 1, it would be negative 1/2, so that would become 3 over root x minus 3 over 2 root x, like that.
Perfect.
Okay.
Yeah, nicely done. If we wanted to, we could have a common denominator between those. The denominators are already so close, it's not too hard, but you can leave it like this, especially since we're out of space on the page. This is a nicely done calculation.
And then this next example, does anyone have any questions on this?
Yeah, so take a second, guys, and make sure you get this into your notes nice and clear. These examples will be helpful to follow along as you're working in the homework. You can see that it's really the algebra that gets intimidating here more than anything else, right? Each of our little derivatives, they're coming from the power rule, they're not that bad. But when we start mashing them together like this, we can end up with pretty complicated algebra expressions. And you just have to be very patient grinding out the algebra, making sure every step you write down follows correctly from the previous step. But as long as you're super patient, super careful, these are not that bad.
I want to explain this one a little bit more, because I kind of just, I got help and I kind of just did it in my head. So 3 root x over x is going to, move that up so that's still there, root x over x. So 3 times x to the 1/2 over x. You can bring this x up, and that would equal 3 times x to the 1/2 times x to the -1. When you combine those, it would be 3 times x. You would combine these two, it would be 1/2 minus 1, which is -1/2. So now with that, 3x to the -1/2, the x goes down, 3x goes down, x to the 1/2, which equals 3 over x, like that. And then for this one, it's just the x cancel. So the next example is from the book, and we're gonna use a graph with this too. So that is a new piece of paper. So there, okay. So next example is from the book. You can find it on page 187 in the textbook. So let's say that y equals e to the x over 1 plus x squared, and trying to find the tangent line at point 1, or no, trying to find the slope of the tangent line at this point. So you can see that we're going to use the quotient rule for this, because it is e to the x being divided by 1 over x squared. So y prime low x plus 1, x plus 1 plus x squared, low d high, use prime notation for this, minus high e to the x, d low 1 plus x squared prime, all over low squared, like that. So then we can derive 1 plus x squared equals the derivative of e to the x is e to the x minus e to the x times, okay, derivative of 1 is 0, derivative of x squared is 2x, all over 1 plus x squared squared. And from there, we can multiply y prime. So e to the x times 1 is e to the x. E to the x times x squared equals x squared e to the x minus So e to the x times 2x is 2 e to the x, since it's negative, or since it's being subtracted, minus 2e to the x, like that. Wait, no, 2x e to the
Yeah,
x.
very good.
Yep. 2x e to the x, like that. And then from there, all over, so again, 1 plus x squared, all squared. You can factor out, all these terms have an e to the x. So you can factor out an e to the x. E to the x times 1 plus x squared minus 2x all over 1 plus x squared squared. So from there, where did that go? So there's a pattern with these. You can rearrange the terms for this one. So it equals e to the x times x squared minus 2x plus 1 over 1 plus x squared. 2. And then this can be factored. Not factored. What's the word? Is it factored?
So the bottom there is irreducible, I think. 1 plus
Yeah,
x.
this can be reducible. So y prime, this is reducible, so it would be e to the x. That's the word I was looking for. What was that? 1 minus be x minus 1
Mhm.
x minus 1 squared.
Great.
All over 1 plus x squared squared. Does anyone have any questions so far? So this is our slope function. This is how we're going to find the slope. So we're trying to find the slope at 1 or 1/2, 1/2 e. So we just plug in those values. You just plug in, so yeah, you just plug in that 1.
Mm-hmm.
So y prime equals e to the 1 times x, or times 1 minus 1 squared over 1 plus 1 squared squared. That's going to equal e to the 1 times 0 squared all over 1 squared is 1 plus 1 is 2 squared. So that 0 squared is 0 times e to the 1 is 0 over 4. So that means the slope is 0. And so if we graph these functions, go to our table. So if we put in the original function of e to the x over 1 for x squared, and then we put in our, what function was that? 1/2 e to the 1. Yes. Well, we can also make our tangent. Actually, no. So is this going to keep reflecting? Let me see something. If I turn off the light, reflect. Okay, that's better. So we can see that when we trace this, we have our function of e to the x over 1 plus x squared here. So then if we look at x equals 1, you have y, which equals this number, 1.359. And that number is equal to 1/2 e to the 1. Then when we go to our slope function, our tangent function, or yeah, our tangent line, the slope of that line is 0, and it has the same value throughout it. So I'll show you. If we do 1/2 times e to the 1, you get that 1.359 number.
Yep, so you can see on the graph there that the tangent line really is horizontal. So the slope of that tangent line really is 0. That's a nice verification.
Okay. And then another example. You don't always have to use the quotient rule every time. There are some times where things can be done easier using the chain rule, but we haven't learned that yet. Are there any questions so far on any of this? Okay. I'm just going to do another example. Let me see. Let's say, this one's going to be a little tougher because it's going to have more parts to it. F of x equals x squared plus x minus 2 over x to the third plus 6. So f prime of x is going to be low d high minus high d low all over low squared, like that. F prime of x. So now we can derive x to the third plus 6 times x squared. Derivative of x squared is 2x. Derivative of x is 1. Derivative of 2 is 0. And then minus x squared plus x minus 2. Derivative of x cubed is 3x squared. Derivative of 6 is 0. All over x cubed plus 6 squared. F prime of x. Okay, so now we need to factor. So we can just ignore the zeros because those don't count for anything. So basically, x to the third plus 2x is 2x to the fourth. X to the third times 1 is x to the third. 6x, so 6 times 2x equals 12x. Then 6 times 1 is 6. Minus. So x squared times 3x squared is 3x to the fourth. X squared times 0 is 0. 3x squared times x is 3x to the third. Negative 2 times 3x squared is negative 6x squared. All over x to the third plus 6 squared. then you would combine those two, f prime of x. So 2x minus 3x is going to be negative x to the fourth. X to the third minus 3x to the third is going to be negative 2x to the third. 12x minus nothing that, there's nothing that affects that one. So it would just be plus 12x. 6, nothing affects that one either. There's nothing to subtract from that. So plus 6, and then minus the 6, or it's going to be plus the 6x now, the 6x squared, because it's a negative here. All over x to the third plus 6 squared. We can rearrange these terms. F prime of x equals negative x to the fourth minus 2x to the third plus 6x squared plus 12x plus 6 all over x to the third plus 6 squared. And so there's nothing you can really do. Even if you factor this out, this is the most simplified it's going to get. So are there any questions about how I got this?
Yeah, this is a reasonable example. These problems can get somewhat overwhelming. And if we were very, very lucky, we might be able to factor that top or do something to clean it up. But this looks like pretty much all we can hope for here. In parting, I think it may be worthwhile to say that some problems you need the quotient rule to solve, and others it may look like you need the quotient rule to solve, but you do not. Thomas, do you mind if I take back over for just the last couple minutes here?
Sure.
Thank you so much. You've done a really great job. I'm going to turn on my screen share, which will steal back from you. So to look at one last example before you guys head out, Thomas has done a really great job here. There's just one point I want to make. Since the quotient rule is a bit rough, we want to avoid it if possible. And so something like this, I want to find the derivative of, maybe x squared plus 2x minus 3 square roots of x all over x. This could be differentiated using the quotient rule. I could use, the f over g primed equals low d high minus high d low over low low, with f of x equal to the top, x squared plus 2x minus 3 square roots of x, and g of x equal to x. Or I can use algebra first. So here, the function I'm trying to differentiate this could be split up as x squared over x plus 2x over x minus 3 root x over x. And then each of those pieces, x squared over x is just x. 2x over x is 2. And 3 root x over x is 3x to the negative 1/2 when we simplify. And now this, I think we would all agree, is pretty easy to differentiate. The derivative of x is 1, the derivative of 2 is 0, and the derivative of 3x to the negative 1/2 would be minus 3 times negative 1/2 times x to the negative 3/2. So for my money, this is the way to go, right? This is 1 plus 3/2 x to the negative 3/2. I would way rather do this than all the work that would be necessary to find and simplify this. So wherever possible, look to see if you can clean things up using algebra first. If you can rewrite your quotient as a sum or difference of power functions, then you can use the power rule. And that is always faster, easier, and most importantly, less likely to make mistakes than writing down a big quotient rule thing and trying to simplify it. So that was the only little extra thing I wanted to inject there, is that whenever possible, try to avoid the quotient rule. Try to just use some algebra and rewrite as a power function or sum of power functions if possible. Many of the examples, in fact, pretty much all of the examples we saw today required the quotient rule. And so they're good examples. They're problems where you need to use the quotient rule. But you'd be surprised how often, especially once, like Thomas said, especially once we have the chain rule, you'd be surprised how many times you might first think you need the quotient rule, but really, if you're a little clever with your algebra, you can escape it. So I would keep that in mind as you work through this week's homework. And then I'll hand it back to Thomas. Do you have anything else we wanted to say before we wrap up for the day?
No, that was all. That was my last example. If anyone had any questions or wanted me to work out anything different, I could do that. But
Any questions for Thomas, gang?
Good job doing all the math live. I definitely wouldn't feel comfortable doing that.
It's very high pressure. Yeah, you did an excellent job. I'm really very proud of this. This is coming out very nicely. So you deserve that. Congratulations, indeed.
thank you.
Congratulations.
But yeah, those were all my examples. Tried to incorporate as much as possible without going into other lessons that involve trig or that involve the chain rule or anything like that. So
We'll get to those soon. We will. So our next few lectures, we are going to start on trig derivatives this week. That's our lecture for Friday. And then we will be moving on from there. Next week, we will talk about the chain rule and a little bit more about trig derivatives, and we'll see how those things all interact with the product rule and quotient rule. And then we will be ready for our first test. So about midway through next week, I'm going to send out the study guide for exam 1. And then exam 1 will likely not be next week, but at the start of the following week. I'll talk more about that Friday of this week and Monday of next week as we get a little closer. So guys, please keep working on that homework. If you need more time on anything, don't be shy, submit an extension request. I'll get in there and grant it right away. Thank you again, Thomas, for carrying us through section 3.2 today. You did a wonderful job, and I know how high pressure it is trying to deliver a live lecture like this. So really wonderful work there. And thank you guys all for attending. I will see you guys on Friday.